Hello dear viewers, this is Dr. Aisha Nazuk here. Today I am going to cover chapter 7 of Gujarati and Porter book, and those of you who are following this playlist from the beginning, thank you for watching all the lectures, and to all the viewers who have landed first time on this channel, you are more than welcome to explore different learning resources on this channel. This channel, Rao Hub, which is managed by myself, that is Dr. Aisha Nazuk. I am a PhD in statistics and currently I am serving at NAST University as an assistant professor at the Department of Economics. This channel have a variety of playlists, like for example some of the playlists are on probability. There is a playlist on introductory concepts of statistics, and then we have two playlists on econometrics, and we have some very interesting playlists as well. For example, we have playlist on positive thinking, on human behavior, and by the way, I have an interesting playlist on humor and comedy genre as well. So coming to specifically about today's lecture, as I said, this is about or this is relevant to chapter number 7 of the book that we have been following throughout this playlist, which is Gujarati and Porter book. This book can be easily downloaded from the Genesis library. If you want to learn how to download books from the Genesis library, I'll post the link of the video that you can watch and see how you can easily download books from the online free library. So chapter 7 of Gujarati and Porter book is about multiple regression analysis, and we'll talk about how to estimate multiple regressions, regression, what are its assumptions, and then what are the relevant concepts that are associated. For example, we'll talk about the concept of R square and adjusted R square. We'll discuss the idea of comparing different models. Then we'll discuss the concept of partial correlation coefficient, and we'll do some solved exercises of this chapter. Okay, so the three variable regression model is actually the case when the dependent variable is of course 1, yi is our dependent variable, whereas x2 and x3, these are our two independent variables. So currently we are focusing on the case we have only two independent variables, although we can have more than two, but just to first set the foundations for the multiple regression, currently we are limiting ourselves to the case of two independent variables, that is x2 and x3, in the equation that is shown here. So we can also write this equation. By the way, in some of the books or in some of the settings, you may see that this equation is written as follows: yi is equal to beta 1 times x1i plus beta 2 times x2i plus beta 3 times x3i, where this x1i is 1 for all the values. For example, if this is 1, of course beta 1 into 1 becomes beta 1. So why we are writing in this form, this will be further clarified once in the later videos we cover the idea of regression through matrix notation. So once we cover that topic, you'll see that this form of writing intercept is relevant or useful. Anyhow, whether we write the equation in the first form or here in the second form, that doesn't make a lot of difference for now. The important thing here is how to interpret these beta 2 and beta 3 values. Beta 1 is same as we already did. Beta 1 is just the intercept, which means in this case beta 1 is the value of the dependent variable when x2 and x3 are 0, right? And that is why we call it intercept. In other words, this is the usual interpretation of intercept, is that this is the average effect of omitted variables on the dependent variable. In other words, average effect of the variables that are not included in this equation, but they can impact the dependent variable. It is stored in the intercept. As far as the slope coefficients beta 2 and beta 3, we call these as the partial slope coefficient or the partial regression coefficient. So we'll learn shortly how to interpret these slope coefficients. So for now we can get ourselves acquainted with the terminology that the beta 2 and beta 3, they are called the partial regression coefficients. Okay, so before I further comment on how to derive the value of the partial regression coefficients and how to interpret them, let's discuss the important or the pivotal assumptions of the multiple regression. Many of these assumptions are similar to the assumption of the bivariate regression model, and a couple of assumptions you'll see that they are new because of the case that we have more than one independent variable in the model. The first assumption in the model is linear or linear in parameters. You can easily recall that this is the same assumption that we made when we were studying the bivariate regression model. That is the case when we had one dependent variable and one independent variable. So anyhow, the first assumption is that all the parameters, they are linear. By now I expect that the viewers who are watching this video, they have the concepts of what is meant by the term linear in very quick and simple way. If anything has a power of 1, we call it linear. The second assumption is that the independent variables values are fixed and they are independent of the residual term. And that is, the covariance between the residual term and the independent variables is 0. So for example, if I go back to this equation form, what the second assumption is saying that there is no correlation or covariance between x2 and ui. Similarly, there is no correlation between x3 and ui. And why we make this assumption is because of the fact that if ui is purely random or purely stochastic, then it should not be correlated with one of the independent variables in the model. So the second assumption is the x values are fixed, that is, they are fixed factor, they are not random factors. I have already covered the concept of fixed factor and random factors in previous videos. If you like me to post the the URL of that video where I discuss the concept of fixed factor and random factor, you can post in the comment section and I'll respond accordingly. Anyhow, the second assumption is that the x variables are fixed factor and the x values or the x variables are independent of the error term. Mathematically speaking, that the covariance between the error term and the independent variable is 0. Then the third assumption is that the expected value or the mean value of the residual term is 0. That is, the expected value of the residual term for any given values of x2 and x3, the mean is 0. So we can also call this that the conditional mean of the residual term. Why conditional? Because it is for given values of x2 and x3 so conditional mean of ui is 0. I have already commented on this concept, why we say that the random error term has a mean of 0, but I'll quickly comment here that if an error is random, then in the long run it should vanish. I mean, if there is some errors is committing randomly, then it's going to cancel out its plus and minus, and it will become 0 in the long run. So that's why expected value or the mean is 0. The fourth assumption is homoscedasticity or constant variance. I have also covered what is meant by homoscedasticity in previous videos. Once again, you can request for the specific URL of that video. Anyhow, the simple meaning of homoscedasticity is that the variance of the residual term is a fixed quantity, and we call that fixed quantity as sigma square. Fifth assumption is that there is no autocorrelation between the random error terms, that is, covariance between two different random errors is always 0, right? You know that if we have, for example, the different values of the residual series, then we calculate the covariance between different residuals, that covariance should be 0. So I have also discussed on this assumption about autocorrelation in the previous videos. You can watch the video to discuss to understand in detail what is meant by the problem of autocorrelation and how we can graphically check whether autocorrelation problem is there or not. Anyhow, we will also post detailed videos on the cases where these assumptions are violated. For example, if assumption number 4 is violated, how we can address that problem. We'll have an upcoming video on that. We'll have another video where we'll see what are the consequences of the violation of assumption number 5 and so on. So many of these assumptions will be violated in the upcoming videos, and we'll see how we can handle the consequences of such violations. Assumption number 6 is that the number of observation must be greater than the number of parameters to be estimated. By the way, I also discussed a rule of thumb here that n, that is the sample size, must be greater than or equal to k plus 1 whole square, where k is the number of independent variables in the model. So although this assumption number 6 says that n must be greater than 3, but many researchers have said that n should be greater than or equal to k plus 1 whole square, where k is the number of independent variables. So in this setup, currently we have two independent variables. So 2 plus 1 is 3 and 3 square is 9. So the minimum sample size required will be 9 to run a model having two independent variables, right? So along with assumption number 6, you can note in parallel that instead of n being greater than number of parameters, it's better that n is greater than or equal to k plus 1 whole square, where k is the number of independent variables in the model. The seventh assumption is that there must be some variation in the values of x variables. This assumption simply says that none of the variables should be a constant. Of course, because if something is constant, we cannot treat that as something which is of course changing and something which could influence the dependent variables. So the x variables should have some variation. Then the assumption number 8 is no exact collinearity between the x variables. Now what does that mean? It simply means that the correlation between x2 and x3, that correlation should not be very high. When I say the word no exact collinearity, it means that there should not be any exact linear relationship between x2 and x3. What does that mean? For example, let me discuss here. Let me open Paint and I'll tell in very easy word. For example, if this is the scatter plot and suppose that this is x2 and this is x1. Suppose that I plot the values of x1 and x2 against each other, and the values are so that they are all exactly lying on this straight line, suppose, right? if all the values of x1 and x2 lie on this straight line, that means there is an exact linear relationship between x1 and x2. So this is what the assumption is saying, that there should not be any exact linear relationship. And by the way, why we are interested, or why we are focusing that there should not be any exact linear, or in fact strong linear relationship between x2 and x3, because if you look at the original equation, if there is a correlation or a strong correlation between x2 and x3, then the interpretation of beta 2 and beta 3 becomes very difficult. We will shortly learn that beta 2 is the partial impact of x2 on y, beta 3 is the partial impact of x3 on y. But if x2 and x3 are correlated, then these beta 2 and beta 3, we cannot say that they are partial impact of only x2. For example, if x2 and x3 are correlated, then beta 2 will have effect of x2 as well as some effect of x3 in it. So this is the reason we say that there should not be any strong relationship or correlation between an x2 and x3, so that we can easily interpret beta 2 and beta 3 as partial impact of the respective variables they are attached with. Then assumption number 9 is that there is no specification bias. Now what does that mean? It simply means that the model is correctly specified. That is, for example, if I refer back to the last video where I introduced the cases where we were applied log on dependent variable, or on independent variable, or on both of dependent and independent variables. So there are different types of specifications. I mean, this is a fully linear specification. We may have a specification when we have a log on y. We may have another specification when we have log on the independent variable, and so on. So what the assumption number 9 is saying, that whatever the correct form of the model, whether it's simple y simple x, or for example log y log x, so whatever the correct specification, we are using the correct form of the model. We will also discuss in our upcoming videos what are the consequences when we do not choose a correct or when the model is not correctly specified, what are the consequences and how we can identify that. Anyways, so when I was talking about, there's a little bit explanation about the assumption of multicollinearity, although I have also diagrammatically commented on what is meant by the problem of multicollinearity. So one important aspect that you have to keep in mind, that when we talk about problem of no multicollinearity, or the assumption of no multicollinearity, it means that we are saying that there is no perfect linear relationship between the two variables. I mean, there could have any non-linear relationship. For example, if the x3 is equal to x2 square, this won't violate the assumption of no multicollinearity, because this is a non-linear relationship. So when we say that there should not be any multicollinearity, it means that there should not be any linear link between the two independent variables, right? If the link between the two variables is, for example, this type, this won't cause any issue with the model estimation. Anyhow, for currently, I don't assume that or I don't expect that the viewers of this video will have an idea how we can check whether the relationship between the two independent variables is linear or not. The reason why I have discussed this issue here is, theoretically you must understand that whenever we say that there is no multicollinearity, it means that we are saying that the two independent variables have no linear link between them. Next, we will discuss the interpretations of the multiple regression equation, that is how to interpret these beta 2 and beta 3 values. So because intercept is generally of lesser interest, so we will focus on the slope coefficient or the partial regression coefficients. So if from the original equation, if I skip the residual part, ui part, you know that this is an expected value of y for a given value of x2 and x3, which we sometimes also write as y hat, or the predicted value of y for a given value of x2 and x3. So the regression coefficients, as we already said, beta 2 and beta 3, they are called the partial regression or partial slope coefficient. Now, how to interpret? Beta 2 measures the change in the mean value of y per unit change in x2, holding the value of x3 constant. So that simply means, let me word in relatively simpler or phrase in relatively simpler words. If x2 changes by 1 unit, and then we expect that on average y will change by beta 2 unit, and our assumption is that we are holding x3 constant. In other words, keeping or ignoring the impact of x3, if x2 changes by 1 unit, the value of y or average value of y is expected to change by beta 2 unit. So the only thing that you have to keep in mind here, that once you are interpreting beta 2, the additional thing, the usual interpretation of slope is relevant here, but just one additional condition, that we are saying that we are holding the impact of x3 as constant. Similarly, once we interpret beta 3, we will hold the impact of x2 constant, or we will ignore it. Now the question arises that how we can in practice do. Theoretically, it's easy to say that we can hold the value of one variable constant. So mathematically, or in regression equations, how we can hold the influence of a regressive constant. So let me explain using one example. Let's say we have data on child mortality, and the variable y represents child mortality or CM, x2 represents per capita GNP, and x3 represents female literacy. Now let us suppose that we want to hold the influence of female literacy constant. The regression equation is that child mortality depends upon per capita GNP and female literacy rate. Now suppose that I want to hold the influence of female literacy rate as constant. We know that female literacy rate will have some impact on child mortality as well as per capita GNP. The dependent variable is child mortality. So for example, it's clear that the female literacy rate will influence child mortality rate. That is why this is there in the equation. But how we can, it will have impact on child mortality as well as per capita GNP. So how we can remove the linear influence of female literacy rate from child mortality and per capita GNP? What we'll do is we'll run two separate regression. First we'll run child mortality on female literacy rate, and then per capita GNP on female literacy rate. So the point is, whichever variable whose impact you want to hold constant, you run the regression of the other variables on that variable. Here I want to hold female literacy rate constant, so I am regressing the two variables one by one on female literacy rate. So suppose that we have these two equations. After we have the data and we run the regression using by now you know that how to run simple regression where we have one independent variable and one dependent variable, so you can easily calculate these values. So for now just ignore the second row, that is the standard error and so on, so focus on the first line. So we have these two equations. This is child mortality rate regression on female literacy rate, and this is per capita GNP regression on female literacy rate. Now we have the residual term. U1I is the residual term from the first model, and U2I is the residual term from the second model. Now what we are going to do is, once we have data on the residual term, now what we are going to do, we will regress the residual term from the first model on the residual term from the second model. What does that mean? I mean, for example, in the beginning, let me comment here again. Let's say in the beginning we had 10 pair of observation for all three variables, that is the child mortality, female literacy rate, PGNP, and female literacy rate, that's the same. So we have three variables. So let's say we had 10 10 values on each of these three variables. So let me write here in Excel as well. Apology that you have to wait a bit. Once my Excel opens, I'll discuss what exactly am I saying here. So what am I saying? That we have, suppose, data on child mortality rate, we have data on female literacy rate, and per capita GNP rate. So suppose I'm just hypothetically entering any number just for the sake of make you understand how that data this discussion is being relevant. So we have, for example, this complete data on child mortality, female literacy rate, and per capita GNP rate. So if we run a regression, for example, which two regression? First we have to regress CM on FLR. So once we regress CM on FLR, we have the residual term. So this one is U1 hat. Right, so this is U1 hat. By the way, it's very easy to calculate residual directly in Excel, but you should also know how to manually calculate U1 hat. U1 hat or the residual is equal to actual value of the dependent variable. I mean, let me write here, this is actually actual value of dependent variable minus the fitted value or the estimated value of dependent variable. So you can easily calculate U1 hat. So my first regression is CM and FLR. So I can select these values, I can click on data, and then I can click on data analysis. Once I click on data analysis, I have this option of regression. So I can click here on regression. So I have to choose Y variable range. So I'm choosing this column, and then X range. So I'm going to choose FLR. We have different options that we can store residuals, and so I click on residuals, and by the way, here this will be stored in a new worksheet apply. So I click OK, and now you can see that we have these three residual values. So I can copy these residuals and go back to sheet 1, and this is U1 hat. Anyhow, similarly you can calculate U2 hat as well. So if you have values of U1 hat and U2 hat, then you can run another separate regression, where this time you are going to regress U1 hat on U2I hat. That is, you are going to treat U1 hat as dependent variable and U2 hat as independent variable. Then you will have another regression output, and you will notice that the slope coefficient this time, this slope coefficient, this gives the true or the net effect of 1 unit change in per capita GNP on child mortality, right? Or the true slope of child mortality with respect to per capita GNP. because now we have isolated or made the impact of female literacy rate as constant by following the process that we have just done. So now this slope coefficient is a true effect of 1 unit change in per capita GNP on child mortality rate. Now the question is, do we have to run this entire multi-step procedure every time when we have to interpret um, the partial regression coefficient? The answer is we don't have to do that. The reason I explained the entire procedure was to help you understand what is the actual meaning of holding one variable constant. But we can easily do this entire procedure of holding variables constant in the discussion that will shortly follow when we cover the idea of partial correlation coefficient. So shortly in coming few slides you will learn that how we can calculate the partial correlation coefficients directly, and there will be no need to follow this entire multi-step procedure. Now let's focus on ordinary least square and how we can calculate the partial regression coefficients. So we were discussing the idea when we have one dependent variable and two independent variable. So you know that the idea of ordinary least square is to minimize the sum of squared residual. So we need to minimize the sum of squared residuals here, just like we did for the bivariate regression model. So now you know that the normal equations or the idea of developing normal equation, how is it done? I mean, first we are going to differentiate with respect to beta 1 and then we'll equate it to 0, then differentiate with respect to beta 2 and equate it to 0, and so on with respect to beta 3 and equate it to 0. Anyhow, those of you who are interested in the complete derivations, the mathematical derivations, or they are for the students of NAST who are currently watching this video, that the complete mathematical derivations are not included in your course because this is an economics course, and generally speaking we leave it for the advanced courses. But anyhow, general viewers who are interested, they may refer to Appendix 7A of Gujarati and Porter book, and where you can see that the complete derivations are given. Anyhow, what we are going to focus here is the one by one, what are the values of intercept and the slope coefficient. So intercept is simply equal to y bar minus beta 2 hat times x2 bar minus beta 3 hat times x3 bar. So if you recall, once we had the bivariate regression, we simply had this beta 1 hat equal to these first two terms. So now we have a third variable x3 in the system, so that is also being subtracted once we calculate beta 1 hat. So this is intercept y bar minus beta 2 hat times x2 bar minus beta 3 hat times x3 bars. And I hope that you can easily recall the fact that bar simply means mean. So y bar means mean of y, x2 bar means mean of x2, and so on. Then beta 2 hat is equal to sum of yi xi. You can notice that these formulas given here are in deviation form. So yi means the mean of y is subtracted from it. So if you have to calculate beta 2 hat, you have to calculate deviations of y, then deviations of x2, then deviations of x3, and so on, and then you have to apply this formula to calculate beta 2 hat and similarly beta 3 hat. One important measure or statistic that we will need here is the variance of the residual term. This is equal to sum of the squared residual divided by n minus 3. And why are we dividing by n minus 3? Because we have 3 parameters in our model. 3, that is beta 1, beta 2 and beta 3. So this is the variance of the residual term. Next we'll discuss the idea of multiple coefficient of determination or multiple coefficient of correlation. So we will see how mathematically we can develop the equation for correlation coefficient and how we can interpret. So referring back to the original equation that we have been discussing in today's lecture, this is the original equation. I can write apart from this u I had, these first three terms, these are actually fitted value of y. That is, if we have to find fitted or predicted values of y, and then apart from this residual term, the first three terms are fitted value of y. So I have written y hat plus ui hat. So if I can write, switch this equation into its deviation form, then I can write small yi is equal to beta 2 hat times small x2 2i and so on. So this is the deviation form, and in deviation form I have written this as yi hat plus ui hat. So then we apply summation after taking square of both sides. So sum of yi square is equal to sum of yi hat square plus sum of ui hat square plus 2 times sum of yi hat ui hat. So that is simply the formula of a plus b whole square. But we know that there should not be any correlation between the dependent variable and the residual term, because the residual term, as we said, that it should be purely random. So sum of yi hat times ui hat is 0, and we have the first two terms left in this equation only. So referring back to the original equation, what is the value of sum of ui hat square? I can easily find sum of ui hat from the original equation, that is yi minus yi hat. So what I have done here is I have switched the values of ui hat square in deviation form. That is, referring back from here, ui hat is equal to yi minus beta 2 hat times x2i minus beta 3 hat times x3i. So I have put this here, and I can simply rearrange this. I can call that sum of yi square is equal to sum of yi hat square, or in other words, I can simply write that this part, sum of yi hat square, this is the sum of squared of the predicted values. So we can say that this is the explained sum of square, right? So this is explained sum of square, and it is equal to sum beta 2 hat times sum of yi x2i plus beta 3 hat times sum of yi x3i. So you can simply see that this equation can simply help us understand the idea or the notation or the equation for the explained sum of square. So we know that by definition correlation coefficient is defined as explained sum of square divided by total sum of square. So we have just proved that explained sum of square is equal to this quantity. So that means that we can substitute this value of explained sum of square here, and total sum of square is simply sum of yi square. So this is the formula for r square, or the multiple correlation coefficient. So r square can be easily computed. Why? Because all these quantity, you have the data on y, on x2 and x3 and so on, so you can easily calculate the correlation coefficient. Of course, for that, first of all, you need to calculate beta 2 hat and beta 3 hat, and you can use the formulas that we have just discussed in the previous slide, how to calculate beta 2 hat and beta 3 hat. So after calculating these betas, you can easily calculate r square. So r square is just like the bivariate case. It lies between 0 and 1, and the model is said to be generally speaking better if the r square value is closer to 1. Next we will discuss the idea of r square and adjusted r square. The problem with r square is even if you add an irrelevant variable in the model, r square is going to increase. I mean, for example, you have a variable which is totally irrelevant to your dependent variable. Just try adding that in your model and you will see that r square will increase. So we define an alternative formula, adjusted r square, which will only increase if the new variable that is being added is a relevant variable to explain the dependent variable. So we have just established that r square is equal to explained sum of square over total sum of square, or we can write 1 minus residual sum of square over total sum of square. So these are different form of writing the same thing, the formula of r square. So if I focus on this formula, r square is equal to 1 minus sum of residual square over sum of total variation, that is yi square. You see how we try to adjust it using the degrees of freedom, right? What we are going to do is that we are going to divide the numerator and denominator by its degrees of freedom. So you know that once we calculate the residual sum of square, there are k parameters that are unknown. So if, for example, here in this case, when we have three variables in the model, that is one y and two independent variables, so we have three betas, that is beta 1, beta 2 and beta 3. So we will divide it by n minus 3, right? So that is just a general case where I have written k. So if we have 3 betas in the model, we will divide it by n minus 3, and then the total variation is divided by n minus 1, because the degrees of freedom for the total variation is always n minus 1. Now I am not going to dig deeper into these details, but if you wish to understand, then you can discuss it with me. For now, you can take it as a fact that the degrees of freedom for the total sum of square is always n minus 1, no matter how many independent variables in the model we have, right? So the equation 7.8.2, that is this equation, this could also be expressed as 1 minus sigma hat square. Why? Because we just said that the numerator here, this is the formula for the variance of residual. If we simply put k is equal to 3 here, because as I said that we have 3 betas in this model, so if I put k is equal to 3, so that will be the formula for the variance of residual term for the 3 variable case. Similarly, the denominator is simply the variance of y. So I have written this as 1 minus sigma hat square over sy square. So one important thing that you have to note, that this adjusted r square that we have adjusted by dividing by the degrees of freedom, one interesting fact about it, that the adjusted r square can sometimes be negative, right? So if adjusted r square is negative, practically we interpret or we take it as equal to 0. One important thing that you have to keep in mind, that only r square and adjusted r square are not a sufficient criterion of deciding whether a model is good or not. There are some other criteria that we will discuss in detail once we discuss the topic of model selection. For now, you can see that we have two different criteria mentioned here, the archaic information or AIC criteria and the Amenius prediction criteria. Currently, I am not expecting that you know what are the details of these criteria. The reason that I have mentioned here is solely on the basis of r square and adjusted r square, we can never comment whether a model is good or not. Next we will discuss when and how we can compare two r square values. So two models or in the R square, whether they are adjusted or not, that is the simple R square or the adjusted R square, we can only compare if the sample size of the two models and the dependent variable of the two model is same, right? The explanatory variable may take any form, right? So for example, if we have these two equations 7.8.6 and 7.8.7, so you can see that we have two different representations. In equation number 1 we have a log on y, in equation number 2 we don't have a log. So the computed R square terms cannot be compared. Why they cannot be compared here? Because you see the dependent variable in the first equation is log of y, whereas the dependent variable in the second equation is y, right? So that means even if the sample sizes are, let's say we assume that the sample size for both these equations is same, even then the dependent variables are different, and so we cannot compare the R square values of these two models. That is, if we were to decide which of these two model is good or a good better fit for the data, we cannot decide on the basis of R square or adjusted R square. Next we will do some practice activities from these chapter 7 exercises. Let's say we have data on three variables y, x2 and x3, and we have to estimate three different regressions, yi on x2, then yi on x3, and the third form is yi on both x2 and x3. We have to estimate the coefficients, let's say, and then we will see whether alpha 2 and beta 2 will be same or not. I mean, you can try by using simply these three variable values, and you now know what are the formulas if we have only one independent variable in the model. So you can easily calculate this alpha 1 and alpha 2, or you can rely on Microsoft Excel and you can simply calculate all three type of regressions here. The question is, even if you don't calculate, for example, if I ask you without calculating, can you comment whether alpha 2 will be equal to beta 2? You see, alpha 2 in the first equation is the coefficient of x2 and beta 2 is the coefficient of same variable x2. So what the question is, whether the value of alpha 2 and beta 2 will be same or not. Similarly, whether the value of lambda 3 will be equal to beta 3 or not, because that is the coefficient of x3. Now let's focus. You can verify that the numerical values of different alphas, lambdas and betas are these. You can calculate in Excel or manually, but you see that these values are different. So why these values are different? First of all, referring back, you see, if the equation number 3, let's say we have data on x2 and x3, so here I am assuming both x2 and x3 are important determinants of y variable. So equation number 3 is, you can say, theoretically speaking, the best equation that we can use. That is, if both x2 and x3 they influence y, then we should include both of these in the model. So if I instead of including both in the model, and I run the first equation only where I drop x3, so what will happen? I have introduced a bias in the equation. Why a bias? Because I have dropped an important variable from the system. So that is what is written here, that if the equation number 3 is the true model, and then equation number 1 and equation number 2 both will give me biased estimates. So this is the reason that the values will not be equal. That is, alpha 2 will not be equal to beta 2 and lambda 3 will not be equal to beta 3. In simpler words, the true or the actual model should be equation number 3, because both x2 and x3 are important determinants of y. So if we omit any one of these variables, then we are introducing a bias in the system. So the lesson here is that if we misspecify an equation, then that can lead to biased estimation of parameters of the true model. Next we have exercise 7.19. Here we have data on demand. By the way, this Excel file I have uploaded for the NAS student on LMS and MS team. General viewer can drop me an email and I can email this file. So this Excel file is available on request as well as on NAS official portals. So we have data on a couple of important variables to explain the demand for chicken in United States. This data is stored in table 7.9. The dependent variable is the per capita consumption of chickens. X2 is the real disposable income per capita. X3 is the retail price of chicken. X4 retail price of pork, and X5 is the retail price of beef. Then X6 is the composite real price of all the chicken substitutes, which is a weighted average of real retail price per pound of pork and beef. So let's say we have different types of demand functions. In all of these demand functions, the dependent variable has a log on it, and we have all the logs on the independent variables as well. So it's a double log model. In other words, the slope coefficients can be interpreted as elasticities. So we have different type of representations. So let's say from the microeconomic theory, we know that the demand for a commodity generally depends on the real income of the consumer and the real price of the commodity and the real prices of competing or complementary commodities. So in view of these considerations, answer the following questions. Which demand function among the ones given here would you choose and why? Now look at the variables that the theory is guiding us. From this activity, what we are going to focus on the fact is, whenever we have to compare different models, then the theory should be given importance. I mean, if the theory is saying that few variables are important, then we should notice where or in which of the equation these variables are mentioned. So if I go back here, we have the complete list here, so we can match one by one. The demand for a commodity depends upon real income, right? So what's real income? Real income is X2, so X2 should be in the model. Then real price of the commodity, so real price of chicken is X3, so X3 should be in the equation. And the real prices of competing or complementary commodities, so we know that X6 is the composite index of all the substitutes, so X6 should be in the system, right? So this is the reason we say that model 5 seems to be the best model, because it has all the relevant variable which the theory is guiding us. So model 5 seems to be best as it includes all the economically relevant variables. I mean, you can say that model 4, this also has the data on the substitutes, right? The substitutes are X4, I mean pork and beef, so X4 and X5. I mean, if we have X4 and X5 in the model, still we have data on substitutes. But the problem here, we will shortly see that X4 and X5 they can be correlated. That is, the prices of pork and prices of beef, they can be correlated, or we can have an association between the prices of pork and beef. So model number 5 has an advantage that X6 has data or composite data of all the substitutes, and by taking it in composite form, we have addressed the issue of multicollinearity as well. Model 1, of course, it has no data on substitute, and model 2 and 3 have limited substitute good information. So you can map with the list of these variables one by one and map with the theory that is mentioned here, and you can see that model 5 is the best model in this scenario. Next is, how would you interpret the coefficient of log of x2 and log of x3? You see, what is x2? x2 is income, so coefficient of log of x2 will be the income elasticity, and log of x3 is the price of chicken, whereas the dependent variable is also consumption of chicken. So this is the own price elasticity, that is because we are taking data on chicken's demand or consumption, and we have data on the price of chicken. So in the language of economics, this is own price elasticity. Then part C, what is the difference between specification 2 and 4? So if you look at model number 2, in model number 2 we only have, if you compare model 2 and 4, you see x2 is in both of these models, x3 is also in both of these models, but in equation number 2 we only have x4, whereas in equation number 4 we have x4 as well as x5. So remember that x4 and x5 are the substitutes, that is pork and beef. So model number 2 is treating only pork as a substitute, whereas model number 4 is treating both pork and beef as a substitute. So this is the difference between these two models. Then what problems do you foresee if you adopt specification number 4? To some extent I have already told you that in specification number 4, although we are including all the variables, but the issue is x4 and x5 can be correlated, and we can have the issue of multicollinearity. Since specification number 5 includes the composite price of beef and pork, would you prefer the demand function 5 to the function 4? I have just told you that specification 4 has it has an issue of multicollinearity. So specification number 5 will be preferred because this won't have any issue of multicollinearity, because we are using data on the composite form by definition, referring back, x6 is the composite real price of chicken substitutes. So model number 5 is better. Then part F, are pork and beef competing or substitute products to chicken? How do you know? This is simple, that we have treated them in the equation as an determinants of the price of chicken. If you look at even at the equation number 5, you see we are saying that the price of chicken depends upon the price of the substitutes by storing data in x6. So these are substitutes, right? And why these are substitutes, even you can look at the actual setup of this equation, right? So these should be substitute goods because they compete with chicken as a food consumption product. In part G, we have to assume if the model number 5 or equation number 5 is correct, we have to estimate this model. We have to calculate r square and adjusted r square. Now you have two options, whether you can rely on Excel and you can calculate all these statistics, or you can refer to the formulas in the previous slide and you can calculate. So for now, just forget about standard errors. If you are manually calculating, you should calculate betas, r square and adjusted r square, and then you can interpret those results. So let's say if I have to calculate these quantities in Excel. So I have this data file. So this is the data, the yellow highlighted part. So this is the actual data given. Now what I have done is I have taken log of these variables, because in equation I have the variables in log form. So I have these log of the required variables. So referring back, so in equation number 5 we have to use log of x2, log of x3 and log of x6 as our independent variables. So what I can do is I can click on data, then data analysis, and then regression, click OK. So what I have to choose the value of y variable and x variable. So the y variable range is this L and Y column, so I'm going to select the entire column here, and once we have to choose x variable range, I'm going to click all the x variables here and I can enter here. Then the options are, I can store residuals, I can store results in a new workbook or new workbook ply, that is a new sheet. So let's say I click OK, and I'll have this entire regression results, and you can manually verify that these results are same even if you calculate in Excel or manually. So these results are mentioned here on this slide. So this is the equation which is given. How we can interpret this is the x2. What was x2? Referring back to the list of variable, x2 is the real disposable income. So 0.481, this is the income elasticity. And then what was x3? Now again referring back, x3 is the retail price of chicken, so this is the own price elasticity. And similarly this is the cross price elasticity, where we are comparing the demand for or the consumption for chicken as compared to or in relevance to the substitutes, because x6, remember, is a composite real price of chicken substitutes. So that's how we can interpret these in terms of elasticities. R square is a fairly high number. Similarly, so we can say that in roughly, although I will discuss later in few upcoming lectures that we can never comment on a model goodness solely on the basis of R square or adjusted R square, but for now we can say that if we were to rely on these two criterion, then collectively these three variables, that is log of x2, log of x3 and log of x6, they have explained roughly 98% of the variation in the consumption of chicken data, right? So now you can if you were to comment on the signs of these models, you see the income elasticity has a positive sign, which is theoretically correct, because if income increases you can increase the consumption of chicken. And then x3, as we said, it's the own price elasticity, so if the price of chicken increases, then the consumption of chicken is expected to decrease, so that means that they have correct sign. Similarly, you can interpret the sign of this log of x6 coefficient. So this was about today's lecture. Now regarding the calculations of beta that we have just done in Excel, you can refer to slide number 14 and you can compute betas manually, and then you can verify that no matter whether we calculate in Excel or manually, the results will be same. So one last comment about how to choose an appropriate model. One important thing that you should keep in mind, that we should not set our aim as that we cannot choose a model just on the basis of maximizing R square or even adjusted R square, right? The theory should guide us which form of the model is good. That is, if we have data on, let's say, demand of some product, then economic theory should guide us that which variable should be included in the demand function. Solely on the basis of statistical criteria like R square or adjusted R square, we should not try to choose appropriate or the best model for a particular scenario. Next we have the concept of partial regression coefficient. As we said that once we interpret betas in the multiple regression, we say that they are partial impact. So how we can interpret the partial impact? So let's understand what is meant by the partial impact or the partial correlation coefficient. Let's say if I were to calculate the correlation between y and x2, So if 1 represent y, 2 represent x2, and 3 represent x3. So if I write 1 2 dot 3, that means it is the partial correlation coefficient between y and x2 holding x3 constant. And how we can calculate? This is the complete formula. I don't expect that you are able to derive this formula, but in fact I don't even assume that you should remember this formula. I mean, but if these values are given, you should be able to interpret. For example, if I give you the value of r12.3, you should interpret that this is the correlation between the y variable and x2 variable holding the impact of x3 constant. And if this formula is given, then you should be able to calculate r12.3. So for example, if in this formula, if we have to calculate r12, so how we can do that? We know that the usual formula for the correlation coefficient can be written like this, that we have just reproduced here or mentioned here. So suppose if I have to calculate r12, that will be simply summation of x1I. By the way, this is not x1, pardon, it's a typo, because as I said that r12 is the partial correlation coefficient between y and x2. So this should be y minus y bar into x2 minus x bar. So everywhere where you can see x1 here, this is not x1, this is y. So y minus y bar into x2 minus x2 bar. Similarly, in the denominator we have y minus y bar square, x2 minus x2 bar square. So let me mention here the correction that is required. Let me copy, because so that you won't have this confusion. So this is the formula, but I'm saying here that it's a typo. Instead of this, you should have yi, and instead of this you should have y bar. Similarly, you can rectify the denominator. This should be yi, this should be y bar. So this is what I was mentioning when I told you that there is a minor typo here on the slide. My due apology for that typo. So you are advised to calculate partial correlation coefficients from the table 7.9. That file is available on LMS and MS Team. The general viewers can request for that Excel file. So you can calculate the partial correlation coefficients and see if you are able to use the formulas given here, and you can whether you can calculate these or not, and then you can accordingly interpret based on the definitions that is given here. Then just a side comment here that this table 7.9 or whichever different data table, sometime when we download tables from different websites, they are not separated in different columns. So you can watch my video where we can convert text to column option in Excel, where we can make a data file for any software very easily by copying from different websites or textbooks, and we can easily convert that into Excel table. So regarding chapter number 7, I have enlisted here different exercises that you are supposed to solve. The solution manual is available on MS Team and LMS. So these are different exercises that you should work, and they are important from exam point of view. So thank you for watching today's video. Please subscribe to this channel and keep supporting, keep giving me further input, and let's have a professional collaboration. And thank you for watching, and see you in our next video very soon.